Hi, welcome back to my channel, Theoretical Physics with Mark Weitzman. We're going to continue with video 5B on the Frobenius algebra and group theory in physics. Continuing with our last video in 5A. This will be a short video, and this video will basically be on deeper insights into the projection operators, which we will have use sometime later. So we can transfer the results. By transfer the results, I mean you have to do a calculation, which is done in the book. I'm not going to do it here. To the group algebra. And projection operators by defining. I just want to check one thing here. Okay. By defining EKIJ equal lambda k over n rho k ij. And my rho's and e's sort of look the same, so I'm going to redo this one. Now that's definitely a rho. And so the idea is that for each k, for each irreducible representation, we're going to get a simple matrix algebra. And it's just a simple factor, this factor over here, lambda k over n, that does it for us. So the EIK, EKIJ, satisfy the requirements for the basis elements that we discussed last time of a simple matrix algebra. And for the proof, see Schensted, page 83, and it uses the orthogonality relations of theorem 4. So recapping this, the two-sided ideal VK spanned by the lambda k squared elements EKIJ equals, it's defined as lambda k over n rho k ij is a simple matrix algebra. And each of the elements EKMM, which is equal to lambda k over n, the sum from j equal 1 to n gamma k. Remember, gamma represents irreducible representations, at least gamma k is the kth irreducible representation. AJ inverse is the jth element of the group, however we order them, inverse of it. And we take the element of the irreducible rep and multiply it by the group element AJ. And this is a primitive idempotent and idempotents corresponding to different values of m are mutually annulling. That's what we mean by primitive. So EK M M EK N N is equal to the null element in the group algebra if M unequal to N. Okay. And it's equal to 1, or the identity element of the group, if M is equal to N. Now the element epsilon k is the modulus of Vk and can be written in the following forms. So each epsilon k for the kth irreducible representation is a modulus, and it's the sum of all the primitive idempotents. And we can now write it using our projection operators and go back to the definition of projection operators. Now you can see if we switch the summation times, which we can do because they're both finite. Everything we do is finite right now. Because we have finite sums, we can switch the orders, and now we're going to get lambda k over n, the sum from j equal 1 to n of the character, because we're going to be summing on from m equal 1 to lambda k. So this is just taking the character of the trace, or the character of the matrix. So this is chi k aj inverse aj, and this is also equal to lambda k over n, the sum from j equal 1 to n chi k aj star is complex conjugate of aj. We have this because all representations are equivalent to unitary representations, and if you just take just work out what the definition of the character of a matrix in a unitary representation is, you're going to get the complex conjugates. So that's nice to know. Now, as we showed before, epsilon k is essentially, it acts as the identity in Vk, and annuls elements outside of Vk. So we have like epsilon k a, where a is an element of the simple matrix algebra, or the group algebra. is equal to A epsilon K, and we call this the component of the element A in the kth ideal. So it projects, so epsilon K projects out of an arbitrary element of the group algebra the vector component in VK. We can go even further if we set A equals E. Remember, we always use capital E for the identity element of the group. 90% of what we're doing in this course is notation. I'm sure you've gotten to that understanding if you've gotten this far. The importance in mathematics of good notation and keeping up with the notation, the identity element of the group G. So then we have epsilon K is equal to EK. So basically, the expansion of the identity element of the group is just K equal 1 to R of epsilon K. It's also equal to sum from K equal 1 to R, the sum from M equal 1 to lambda K, EK, MM. So we've now expanded our identity element of the group in terms basically of these primitive idempotents. So using these idempotents or the projection operators, or projection they're related by a simple factor, we can establish an expansion theorem and a dual orthogonal relation. And this is all very similar to what we do in Fourier analysis. Some of you may have heard of doing like Fourier analysis on groups and everything. That's essentially what we're doing. It's an extension of our usual Fourier analysis. So now we have this new expansion. The group element AJ, sum from K equal 1 to R, the sum of CC prime, gamma K, AJ, CC prime, rho K, CC prime, lambda K over N. Remember, this is the jth, let's call it, element of the group G. These are the projection operators. And now we also have the dual orthogonality relation. I say dual because we've established an orthogonality relation before, but this one is essentially dual to that. The sum from K equal 1 to N, sum of CC prime, lambda k over n. What we're doing is essentially inverting this. Gamma k aj, gamma k h inverse. Oh. And this is equal to the Kronecker delta JH. So, as I said, we'll be using a lot of this material in a couple of chapters, and that will finish this video today. I'll go on to some short videos, but eventually we're going to finish this chapter with a discussion of classes, which will require a lot of new notation, and then we'll prove the Frobenius reciprocity theorem, which is a very interesting theorem, which again will be used when we do representations of the symmetric or permutation groups, and when we do the general linear groups and the various subgroups of the general linear groups. Basically what's happening, and this is something that a lot of the physics books, they sort of skim over or they don't do the details, and we'll skim over some details as well. But basically what we're going to find is we're going to have, when we talk about the general linear groups and the subgroups, we're going to find that there's two kinds of commuting operators. There's like the permutation operators, and they commute with the tensor transformations. So the idea of tensor analysis is to decompose the tensors that we get. You know, if you've done very elementary physics, you know, for instance, when you have, let's say, a 3x3 tensor, it's 9 elements, you can reduce it into like 5 plus 3 plus 1. You know, 1 is the trace or scalar element, 3 is the anti-symmetric vector, and the 5 is the symmetric traceless quadrupole. So if you take an electromagnetism, you understand, or even classical mechanics, you've gone through these decompositions for certain tensors. And you know, if you've done special relativity, you have a 4x4 tensor, and you'll reduce it to you know, an anti-symmetric you know, we'll have vectors for like electric and magnetic, and 3 components, and we'll have you know, 6 components when we combine them into the electromagnetic field tensors Fij, and then we'll have the other further decomposition. I'm slipping my mind right now, but the point is, you know, those are just second rank tensors, but third rank tensors, fourth rank tensors, we can also decompose using the symmetry groups, because when you get to higher order, and it becomes a lot more complicated, and when you get to groups like SU3, quark model and everything, these decompositions and direct products and everything will become very important. So I know in this course right now, so far it's been all math, but eventually we will relate it to physics and the quark model and QCD, and if you studied physics, you've already done these things without. It's much easier when you do SU2. Then you don't have to worry about all this stuff when you do addition of angular momentum. But this will sort of solidify that understanding of the addition of angular momentum. And then when you go to higher groups, it's necessary to use this group theory. So thank you for watching. I'll see you next time. Bye-bye.